Okay, now let's see the two important concepts for dilution refrigerator. One is the vapor pressure of helium-3, helium-4 mixture in the steel, and the second is the cooling power of the dilution refrigerator. The pressure of the helium-3 and helium-4 gases floating above the helium-3, helium-4 mixture liquid is known as the vapor pressure. The partial pressure of the gases helium-3 and helium-4 are added to produce this vapor pressure. Nearly all of this vapor pressure source is more volatile helium-3 gas below 1 Kelvin. The vapor pressure of helium-4 is therefore very low because only helium-3 atoms in the steel should be blasted out. This characteristic is crucial in the dilution refrigerator. Let's see this figure. This is mixing chamber, and the mixing chamber is connected with the heat exchange and the steel. And above steel, we have evaporator, and at room temperature, pump is here. Okay. The pipe, two pipe is connected to mixing chamber. One is for recycling of helium-3, and another is pumping the helium-3 atoms. And this pipe is connected to mixing chamber, heat exchange, and the steel, and the evaporator, 1K plate. So basically, we pump out the helium gas, helium-3 gas in the steel. So here, all of the gases in the steel is helium-3 atoms. Most of them are helium-3 atoms. So by pumping, we can extract helium-3 atom only in the steel. Okay. So because only helium-3 atoms in the steel should be blasted out, this characteristic is crucial in dilution refrigerator. So all of this vapor pressure source is more volatile helium-3 gas below 1K. So in the steel, let's see the steel. In the steel, the gases are composed of helium-3 and helium-4, but helium-4 is very small. Amount of helium-3 is very small compared with the amount of helium-3. So in the vapor, 97% of gases is helium-3. Only 3% is helium-4. So we can extract helium-3 only by pumping. So that is very crucial characteristic in the dilution refrigerator. Okay. On the other hand, in the liquid, in the steel, the helium-3 component is very small. Most of them are helium-4. So even though the liquid in the liquid helium-3 is very small, but in the gas state, most of the gases are composed of the helium-3 because helium-3 is more volatile. So in the gas, most of gas is composed of helium-3 atoms. So we can extract only helium-3 atoms from the steel by pumping. So this means that only helium-3 atoms can be pumped out of the steel because the vapor within is almost helium-3 gas. The helium-3 atoms in the concentrate liquid can then be evaporated into the dilute liquid in the mixing chamber, which is connected to the steel by pumping the steel to remove the helium-3 atoms. So by pumping the steel, helium-3 atoms are pumped out. Then mixing chamber is connected to the steel. So in the mixing chamber, helium-3 in the concentrate liquid are evaporated to the dilute liquid. So we can have cooling power. Only 0.7% of the mixed liquid in the steel has helium-3 when it is running at 0.7 Kelvin, so about 1% here. However, practically all of the vapor above the mixture of this liquid is made up of helium-3 gas. So in the gas, most of them are helium-3 atoms. The evaporated helium-3 atoms move to the vacuum pump at room temperature. These atoms should be returned to the mixing chamber for reuse. After passing through the condenser at 1 Kelvin, these helium-3 atoms become liquid. The mixing chamber's temperature, which is millikelvin, is significantly lower than the temperature of these liquefied helium-3 atoms. Thus, we can put this liquid helium-3 at the 1 Kelvin into it. The returning helium-3 gases will become liquid passing through the condenser. So that is a helium-4 part, which is 1 Kelvin. However, the mixing chamber's temperature is mid-Kelvin, so we cannot put these helium-3 atoms at 1 Kelvin to the mixing chamber. Okay, so we must lower the temperature of this liquid helium-3 to near the temperature of the mixing chamber before putting it in the mixing chamber. Okay? Otherwise, the temperature of the mixing chamber will rapidly increase and the phase separation will disappear. As a result, the cooling process will come to a halt. So we have to lower the temperature of returning liquid helium-3 to the mixing chamber as close as possible to the temperature of mixing chamber. Heat exchangers are used to solve this problem. The basic principle of the heat exchange is to transfer heat between cool and hot liquids. The cool liquid is being pumped up from the mixing chamber to the vacuum pump. The hot liquid, on the other hand, flows down from the condenser to the mixing chamber. These two liquids are thermally connected by heat exchanger. We have continuous and step heat exchangers, so two types of heat exchangers. Figure shows several examples of these heat exchangers. Several heat exchangers in the dilution refrigerator lower the temperatures of circulating helium-3 liquid to as near to the temperature of the mixing chamber as possible before entering the mixing chamber. This is the continuous heat exchange, and this is the step heat exchanger. You can see here this is mixing chamber, and we have step heat exchangers, 3 step heat exchangers, and we have continuous heat exchanger here, and here we have a steel, and there is a helium pot to liquefy the circulating helium-3 gas. The dilution refrigerator has significantly helped the studies on physical properties at low temperatures by providing the temperatures in the millikelvin range. It also enabled for nuclear demagnetization cooling. We will discuss this demagnetization cooling later. The nuclear demagnetization cooling technique obtains the lowest temperature ever recorded. That's microkelvin. Okay. This method of cooling will be discussed further. This slide shows some examples of dilution refrigerators. You can see here there is a helium 4 pot. This is the continuous heat exchanger, and we have 3 step heat exchangers. This is a mixing chamber. In this figure, this is mixing chamber, and there is a step heat exchanger and continuous heat exchanger, and the steel is here. There might be steel, and up here we have helium pot. So there's steel and helium pot. And this figure shows the mixing chamber is here, and we have 4 step heat exchanger and continuous heat exchanger, and this is steel, and up here we have 4 pot. Okay. This figure also shows the same structure. There is the mixing chamber and step heat exchangers, continuous heat exchanger. This might be steel, and this is a 4 pot. Okay. Now let's see the cooling power of dilution refrigerator. The heat energy extracted from surroundings per unit of time measured in watt is what defines the refrigerator's cooling capability. The dilution refrigerator operates on the same principles as an evaporator. The relationship, this relationship, is satisfied by the evaporation process under constant pressure. The heat load, which is the same as the heat energy extracted, is given by this equation. If the this relationship is applied to the second law of thermodynamics, this one, So if you use this relationship to the second law of thermodynamics, we can obtain this relationship. Okay. Here, n dot Hb and Hl stand for the amount of gas evaporating per unit of time, the gas's enthalpy. So V stands for vapor, so gases enthalpy, and L stands for liquid, so liquid reservoir's enthalpy. The helium-3 atoms in the concentrated liquid evaporate into the dilution liquid in the dilution refrigerator. The enthalpy of the helium-3 is before being evaporated, so that is in the liquid phase in the concentrated liquid, so there is enthalpy as H3C is thus represented by HL, so there's liquid phase. The enthalpy of the helium-3 that's evaporated as gas in the diluted liquid, so H3D, on the other hand, is HB, vapor, HE vapor. As a result, we can rewrite the equation for the heat rod above this one. So HB is the H3D, so there's a diluted liquid, and HL as concentrated liquid. So there's enthalpy of the helium-3 in the dilute liquid, and this is the enthalpy of helium-3 atom in the concentrated liquid. So helium-3 gas in the concentrated liquid are evaporated into the dilute liquid, so we can have this relationship. Okay. The number n dot here represents the mole of helium-3 atoms that recycle every second. The heat flow in the mixing chamber of the dilution refrigerator is depicted in the figure. This figure, with a mole flow speed of n dot, the recycling helium-3 atoms enter the mixing chamber. So that's N3 dot. Recycling helium-3 flow speed 3 dot is coming to the mixing chamber. Okay, the mixing chamber releases the same amount of helium-3 atoms. So the same amount of helium-3 atoms will exit from the mixing chamber. So this much of the helium-3 enters to the mixing chamber, and the same amount of helium-3 moved out of the mixing chamber. In the equilibrium state, the internal energy does not vary and the system doesn't do any work. Thus, as depicted in the picture, the energy conservation law results in this relationship, which was already seen in the preceding slide. We already seen this relationship. So energy conservation, so we have this relationship. So this heat is input, and this energy is coming in, and this energy is coming out. So we have this relationship from the energy conservation. The enthalpy of the helium-3 atoms in the dilute liquid also depends on XT. Yes, XT depends on XT, which is the portion of helium-3 atoms in the dilute liquid. Let's investigate how helium-3 enthalpies behavior in both concentrated and diluted liquids. The specific heat data of the pure helium-3 liquid at constant pressure can be used to calculate the enthalpy of helium-3 atoms in the concentrated liquid. We have this relationship. Since the heat added to the pure helium-3 liquid at constant pressure is equal to the change in enthalpy. Okay, so we have this relationship. As a result, the enthalpy is written as, so if we integrate both sides, 0 to Ti, we have A30 and this integral. The energy at absolute zero or 0-point energy is here as A30, so there is actually 0-point energy. 0-point energy. This is 0-point energy. Experimentally, C3 is expressed as 24 T joule per mole K square below 40 millikelvin. So enthalpy is described by the equation. If we use here 24 T, then we can have these results. The enthalpy of the helium-3 atoms in the diluted liquid, so helium-3 XDT, this one, can be calculated from experimental data, but the resolution is too low and the value is too small, below 1.1 Kelvin for theoretical consideration. So, since the helium-3 atom is moving close to the boundary between the concentrator and the dilute liquids, so let's use that the moment to determine the expression of enthalpy of helium-3 atoms in dilute liquid. The helium-3 atoms cross the boundary during thermal equilibrium, and the process is reversible. So, two regions' chemical potentials are equal. So we can assume that chemical potentials of helium-3 in the concentrated liquid and diluted liquid are the same. So we can assume this relationship. Since the chemical potential is given as this equation, so we can get this relationship. So we put the H3 concentrated state, so this equation, and we dilute liquid, we have this relationship. So we can from this equation we can have these results. Okay. The specific heat of recycling helium-3 atoms is given by the equation this equation below TF, since the helium-3 atoms in the dilute liquid behave as ideal atomic particles. When the helium-3 fraction in the diluted liquid is 6.3%, the value of TF is 0.38 Kelvin. Okay. If we use gas constant, we get the specific heat of the helium-3 in the dilute liquid is given by 108 joule per mole K square. The entropy of the helium-3 in the diluted liquid is therefore given as this equation. We put this specific heat here, then we have this value. The helium-3 atoms in pure helium-3 liquid have a specific heat of 24 T. We already saw it in the previous slide. As a result, S3T is given by 24 T. So that is the entropy of helium-3 atoms in the concentrate liquid. So S3, this one. We may eventually express the enthalpy of the helium-3 in the diluted liquid as this equation by putting these equations. So we have entropy of helium-3 atom in dilute liquid, and we also have the entropy of the helium-3 in concentrated liquid. So in previous slide we have this relationship. So if we put the entropy here and this one here, then we have this relationship. So there is enthalpy of helium-3 atoms in dilute liquid. So we used this one here. So the previous slide equation was utilized in this case. Okay. So the heat energy required for the helium-3 atoms in the concentrate liquid to evaporate into the dilute liquid is equal to the sum of the 0-point energy A30 of the helium-3 atom in the pure helium-3 liquid, so concentrated liquid, and the heat energy in the dilute liquid, which is equal to this one. So enthalpy of the helium-3 atoms in the dilute liquid is a sum of 0-point energy plus sum of 0-point energy and the heat energy 96 T square. This is the heat energy in the dilute liquid. Okay. This 96 T square is related to the second law of thermodynamics, and we have delta Q. So there is here just for 1 mole of the 1 mole of helium-3 flow, we can have this relationship. So one more time, the enthalpy of the helium-3 in dilute liquid is the sum of 0 point energy plus 96 T square. Okay? So 96 T square is the heat energy in the dilute liquid. The helium-3 atoms in the concentrated liquid that evaporate into the dilute liquid are thus represented by this equation as obeying the second conservation law, obeying the energy conservation law. So we have the enthalpy of helium-3 in the dilute liquid, and we also have enthalpy of helium-3 in concentrated liquid. So we can get the expression for the cooling power. So cooling power is given by this cooling power, this equation. Cooling power is given by this equation. And we already obtained H3D and H3. So we just put this here and this expression here. Then we can have cooling power, this equation, which can be obtained by plugging the expressions of enthalpies in the concentrated liquid and dilute liquid into the equation, this equation. So we can have this cooling power expression. Setting the cooling power to 0 allows for the refrigerator to reach its lowest temperature. So if we put this 0, then we can have the lowest temperature. So minimum temperature is what we have. The cooling power and lowest temperature are both affected by temperature Ti of the recycling helium-3. So Ti is the temperature of helium-3 in the concentrated liquid. So that is the actually temperature of helium-3 recycling to the mixing chamber. So the cooling power and the lowest temperature are both affected by temperature Ti of the recycling helium-3, as can be shown in this case. As a result, it is clear that the heat exchangers operation is crucial for achieving the maximum cooling power and lowest temperature. As closely as possible to the temperature of mixing chamber, the heat exchanger must reduce the temperature of the recycling helium-3 atoms. The relationship Ti is close to T. Ti is the temperature of recycling helium-3, and the T is temperature of mixing chamber. So this relation holds in the one-shot dilution refrigerator. So no helium-3 atom recycling, or the dilution refrigerator with ideal heat exchangers. So this equation means that the temperature of the recycling helium-3 is reduced to the temperature of the mixing chamber due to the operation of the heat exchangers. So that is ideal heat exchangers. So heat exchanger reduce the temperature of the helium-3, recycled helium-3, just the same as the mixing chamber. In these situations, the cooling power of the refrigerators is therefore given as this equation. So T equal Ti, so we can have this equation. So T is the temperature of mixing chamber. Experimental evidence supports this equation. For instance, Vilches and Whitley in 1967 observed that their one-shot ballast refrigerator's cooling power was this value at 12 millikelvin with helium-3 recycling, 10 to the minus 5 mole per second. So 12 millikelvin is the temperature of mixing chamber. So we have for recycling rate, then we can have this cooling power. So we can use this one here. It's very close, but slightly different. But due to the various heat losses that are present in most refrigerators, there is a small difference between experimental and the theoretical values. Their experiment shows a heat loss of roughly 19 milliwatt.